In this video, we're going to look at an alternative to the midpoint rule or the midpoint sum, and that's the trapezoidal rule. So far, all we've used to estimate areas have been rectangles, but there's no reason at all why we can't use something a little more sophisticated. And by a little more, I mean literally just a little more. Imagine on this interval here, from one x value to another x value, we've seen how to build rectangles from the left side. We've seen building rectangles from the right side. But again, that's kind of wasteful. If we already know the height of these 2 points, it might be much more instructive to use an area estimate that is based on connecting those 2 points with a straight line. And as soon as we do that, we see a shape that we recognize, and that is a trapezoid. So a trapezoid seems like a much more reasonable estimate of the area underneath a graph. If it curves a little bit, that's fine, but the straight line is going to be a much better approximation than any flat construction that involves rectangles only. Well, the question is, how much harder is that to work with in terms of our calculations? It turns out it's not too bad. If we want to know the area of a trapezoid, there's a few different ways you can arrive at this formula. The way I like best is to take these 2 points here and go down and try to think out where would the middle point be. If I could find the midpoint there, then what we can do is take this triangle and spin it around. And if we've done our job correctly, this is a straight line, and so if we spin that triangle around, it's going to completely fill the other side of this area. We're going to take this, cut it down, and we're going to end up with this new rectangle. So wait, once again, we're back to rectangles. But that area is going to be equal to something with delta x's. And how would I find the midpoint on this height? Well, it's going to be the average of the 2 heights. Well, it's going to be the average of the 2 heights at the ends. Well, that is just the function value at the left plus the function value at the right. Remember how to get an average. You add 2 numbers together and then divide by the number of things that you're averaging. So our left plus our right on this interval, we go up to the graph, go up to the graph, and if we average those 2 heights, we add them, divide by 2. And that's perfect. This is actually closely related to our left and right hand sums. Let's see how we can generalize that to get a full rule. Generalizing to a number of intervals here, imagine a graph, and imagine building trapezoids on each interval here. And same at the end here. The trapezoidal rule with n intervals is going to be the average of the heights on the first interval using the first point and the second point, x0 and x1, times delta x. Then you do the same thing again using x1 and x2. Average those heights then by adding them, dividing by 2, and so on until we get to the last interval, f of xn minus 1, add that to f of xn, and divide that by 2 to get an average height, and multiply by the width. So that's a perfectly acceptable form for the trapezoidal rule. We can make that nicer in summation notation if we like. We can add up from I equals 1, I counts our rectangle number or our interval number, and we just put xi minus 1 and xi, remember we're adding because we're finding an average of 2 numbers, times delta x. That's a perfectly acceptable short form for it, though it's not as easy to calculate with particular examples. What I like to do is notice this side, if we're actually calculating this for a specific example, notice everything has a delta x. every term had a delta x multiplier, so we can bring that out front. We also have an f of x naught over 2. But then if you notice, we have f of x1 in this term because it's the right end of the first interval, but we also have it in the second term because it's the left end of the second interval. And so what we end up with is 2 fx1s, again, over 2. They all have that over 2 fraction. But that goes away. And then we'd have the same thing happening, 2 f2s over 2. 2's will cancel. And in fact, all the terms, x3 would be on this interval and this interval. x4 would be on 2 intervals on either side. Even x minus n minus 1 would appear in 2 subintervals. The only one that's not going to appear in a second interval, aside from x naught, is the last point, f of xn. It'll stay as just one term over 2. Why would we want this form instead of the other form? Because it'll make a more straightforward calculation. These are the kinds of values we might write down in a table, and if we can add a half of this one plus this plus this plus this plus this, it'll be more straightforward to calculate in our calculators rather than finding one average and then restarting finding another average and restarting finding each successive average. We'll apply this formula a little later in an example. Another interesting alternative, though, is to group our terms from the last page a little differently. If we're talking about the trapezoidal rule with n intervals, let's go back one page and notice that we could gather these terms a little differently again. We could gather f of x naught, f of x1, f of x2, and so on, all the way down to here. Well, that's the left-hand point, the left height, and the left height of the next interval, the left height of the next interval. All of the left heights added together would be this part here. And similarly, this f of x1 is the right-hand height, and the right-hand height on the second interval, and so on and so on and so on. If you notice the pattern there, what we did is we added up the left-hand estimate with all the green elements and including the delta x, that would be the height times width for the left sum. And then the right-hand sum would also have the delta x, we would factor that out. And so we would have the sum of these two elements. Not just that, though, we also have the divided by 2 that we haven't accounted for. But we see the same structure, that the trapezoid rule is an average of two other quantities. The average of the left and right estimates. And again, with that Goldilocks kind of feeling, we would expect that knowing the left has some deficiencies, but the right uses the other information, if we average those two numbers, then we're more likely to be close to the exact answer for the area under a graph. And that here can be constructed by formulas involving the trapezoidal areas joining these points on the graph originally. Again, it's not going to be perfect. There's still going to be some error, some overestimates, some underestimates, but it's going to be, on average, much better than either the left or right sums by themselves. Focusing on the efficiency side again, there's a quote that you'll read in numerical methods textbooks that says, "The trapezoidal rule is especially accurate for functions for which the second derivative of x in absolute value, but let's just say the second derivative of x, is small for all x's." Explain from an intuitive point of view why you would expect this to be correct. Well, just thinking about the second derivative, this is about curvature or concavity. If you have a large f double prime, you'll see things bending quickly. If you see things bending slowly, then the points along this curve have small second derivatives. Well, what do you notice here? This is closer to linear. There's less bend, What's the alternative of bending a lot? The alternative of bending a lot is being a straight line. So if we have just a gentle curve, then if we connect points on this graph with straight lines, then we get very good approximations of the area underneath. So that's just capturing that the idea that the trapezoidal rule is using a linear replacement for our function, and if the function doesn't bend too much, i.e. it's linear itself in the first place, then we're going to get a very good estimate using the trapezoidal rule. All right, let's see this in application. We have a function. Let's draw this out first, where the value is 1, and then at 2 it's 3, and it goes up to 4, it goes up to 5, 4, and 2. So the idea is the function might look like anything. We don't really have much information. But what we can do is ask, what would the area underneath this graph be on the interval from 0 to 10? Our new approach here specified, and it will be specified in any questions what rule to use. Here, using the trapezoidal rule, we would build trapezoids as our estimate for the area underneath this graph. And the question then just becomes, how do we compute that average? Well, fortunately, we have all these table values here. And earlier we saw a little bit of a shortcut for how to compute that average. We have the function at the first point, f of 0. We're going to take half of that. Then we're going to take the function value on the next point, f of 2 for us. Then f of 4. Then f of 6. Then f of 8. And then on the last interval, where the 10 is, we're only going to take half of that height. And remembering where all this comes from, this is our widths, and this is essentially the sum of our average heights. We had the height at 0 and the height of 2 averaged, but then we also had the height of 2 averaged with height of 4, so we would have a double counting of the height at 2 during this process. And this is just a short form that gets us to the calculation a little more easily. Important ingredient, what's delta x? It's the width of each of these literal trapezoids that we've drawn. So that is always 2 in this scenario. And then we can just go down the function values. We have 1, and we have 3, we have 4, we have 5, we have 4, we have 2, and then we don't forget the last one and the first one have that over 2 divisor. Next, we just run the calculations. That gives us 2 and 17.5, and that gives us a total of 35 as our integral value. And again, for a 10 and around 3.5 height, that seems like an entirely reasonable estimate for that integral value. Our next step is to do a lot of practice and just reinforce these ideas, reinforce these formulas, and keep tying them back to the area ideas that really drove our initial construction of integrals in the first place.